just about every class is how many questions are going to be on it. All right, there are probably 4 to 5 topical questions. In other words, separate statements. Of those, there will be multiple parts to each. Now, if you know the quizzes, that's the kind of stuff expected. And all this stuff builds, more or less, the first stuff builds on the second, builds on the third. So, and it's closed book, closed notes. You get your calculators, know how to use any functional. And I'm not going to ask something like this on the exam. And on the final exam, you will see problems at least of the order of difficulty of this one. 3-5.3. So he gives you 2 functions. He says, I got a random variable x of t, and that's just cosine, and he puts it at 100t, but I'm going to put omega t plus some phase angle. I'm going to use theta here. Then he says, I got a y of t, and it's equal to some cosine of omega t plus another phase angle psi. Then he says he wants that equal, and I'll call it some z of t, and that's equal to some a cosine of omega t plus the phase angle, and he uses phi. So he wants this equal to cosine, or really to x of t plus y of t. At first glance, this value's omega is the same in all 3 of those, right? The omega t. In other words, the skew in the argument is the same for all of these. That means you can get rid of it. So get rid of that thing. That's the first thing. He doesn't talk about that, but that's what you can do. Oh, and you can get rid of t, and now it's going to be a function of, it's just a function of theta, and this is just a function of psi, and this is just going to be a function of phi, right here. And this is x of theta plus y of phi. Now, with that in mind, these right there equal to this means I start by getting the value of a here. Now, so if this is x and this is y, but I'm going to start out as saying I have this function right here, cosine theta. On this axis, we can make this have a distance of cosine of theta here. And it means that it also is associated with something in this plane. And you can make it complex if you want. You can call this the real and call this the imaginary axis. And you can say this is associated with something of length 1 and angle right here, theta. Normally they put that e to the j theta. That's what they'd say this is. It's a line right here that would have, it would be just e to the j theta. Does that make sense? The projection is the cosine on the real axis. Next, you're going to have something as an angle like this. Has this, and this is psi. This distance is going to be projected down here, and this distance is going to be cosine of psi. And I'm trying to draw that right. Now, then if you take a look at this plus this has to be equal to, and if I did this right, you would see this would be a radius of a. That would be the actual magnitude of that. And the projection here would be a cosine of phi. Now the height of this would be a sine of phi. Take a look at that for a second and first convince yourself what I've shown you is right. And this should be, this is the actual projection I'm showing there. If I look at the magnitude of a here, a squared is going to be equal to, well, it's going to be this term squared plus this term squared. It's going to be, I know this length is cosine of theta plus cosine phi. This distance here would be sine of theta, sine of phi. So we're going to say a squared would be equal to cosine of theta plus cosine of psi, quantity squared, plus sine of theta plus sine of phi right here squared. Yeah. You're absolutely right. I'm sorry about that. That means a squared here. Just follow me on this. When I go ahead and square this, I'm going to get a cosine squared of theta. I'm also going to get a cosine squared of psi. And then I'm going to get 2 times cosine theta cosine psi. This is going to be equal to, I'm going to stop there just so everybody sees it. What is always sine squared and cosine squared are the same argument? 1. So I got 1 plus 1, that, plus that is 1, that plus that. Then I got plus 2 times cosine theta cosine psi. All right, now I'm going to replace this 1 plus 1 by 2. I'm sorry, when I do this, if you look at this when you go ahead and square it out, you're going to get, of course, sine squared theta, sine squared psi, plus 2 times sine theta sine psi. I forgot that there. So this is that plus 2 times sine of theta sine of psi. Now I come over here, we have cosine of A minus B. That's cosine of A cosine of B plus sine of A sine of B. Y'all remember the trig identity? I get down to this point, what does that mean? Well, I have the cosine and the sine there, right? So that means that's equal to cosine, what I should say, forget the 2, just this term cosine theta, cosine psi, plus sine theta, sine psi. I have cosine of theta, cosine of psi, plus sine of theta, the sine of psi. Now that's equal to cosine, and the order doesn't matter, cosine of theta minus psi. I can rewrite this. A squared is equal to 2 plus 2 times cosine of theta minus psi. Cosine squared of x, that's equal to 1/2 plus 1/2 cosine of 2x. I don't know how many of you remember this one. Anytime you're wondering about these identities, go to Euler's, and if you have, this is not directly related, but it may help you later. If you just have like cosine of theta, well, that's equal to e to the j theta, and then it's going to be plus e to the minus j theta over 2. Do you all follow me? Mm-hmm. Here's how you get all these things. Every single trig identity you can use Euler's identity for the cosine and sine ones at least, and the tangent ones. You can start with Euler's and do the operation. They say now when I square it, now I get e to the j2 theta plus e to the minus j2 theta. And then you're going to get plus 2 over 2. Agree with that? If you look at this right here, it should be this over 2. I should just do this over 2 plus 2 over 2. Well, that is the cosine of what? Of 2 theta, right? Plus 1. Do y'all follow me on this? And then when you square it, this becomes 2 squared, so it's over 2 down here. Follow me? Now look, that's this identity. But back to this thing. This is really going to be what? Well, it's 2 plus 2. And now this is sine and cosine there. That is going to be cosine of theta minus phi, so I'm going to have, it's 2 plus 2 cosine of theta minus psi, and it doesn't matter the order. You could make psi minus theta. Follow me, because cosine's an even function. I'll take the 2 out in front, so I have 1 plus cosine of theta minus psi here, and I look over here, and I can say, if I multiply by 2, now if I have 1 plus cosine of 2 So here I have 1 plus cosine of, this now is twice the angle. Y'all with me? I can replace that whole thing by, I replace that part by 2 cosine squared of half that angle in the argument. Okay. So this is going to be, that is a squared. Y'all follow? Obviously I get a equal to 2 cosine of theta minus psi, or psi minus theta over 2. And here he uses the symbol beta is equal to theta over 2 minus psi over 2. So he says A is equal to 2 times cosine of theta over 2 minus psi, or really beta, just beta. It's fine. Okay, he says both psi and phi are evenly distributed between 0 and 2 pi over the range and 0 elsewhere. So that means both of these functions have this. He's going to say f of theta looks like this. And you can go from minus pi to pi. Here I'm going to go 0 to 2 pi. So if you look at the solutions, it will make sense, 1 over 2 pi. And that's the same thing as f of psi. So the argument here could be theta or psi. He looks at what beta is, right? It's this and that. So he creates functions that are f of theta over 2. And actually he has f of theta over 2. Same thing as f of psi over 2. I mean, that's where the angular function is divided by 2. And those are uniformly distributed too, but they only go from 0 to pi, and they have a height of 1 over pi. And this would be the argument in this direction would be either theta or psi. Does everybody agree with that? Now, we go to the next part. Here's where you're going to be doing convolution. So he wants the probability of A being greater than 1. So A is equal to 2 cosine of, here's the way I do it at least, cosine of, beta, and it has to be greater than 1. Right? So now I'm going to just divide by 2. That means cosine greater than 1/2. So now what you have to do is actually get familiar with the trig functions, because if it was a sine, it would be different. And if it was a tangent, it would be different. This is the thing. This functional form, you kind of have to know these trig forms. If you look at this, if you graph beta here, and you graph cosine of beta here, you know it has a value of 1 here, and then it does this. Now, I'm only going over 1 period. So this would be pi, this would be minus pi. I always like going from minus pi to plus pi when I do trig stuff. A lot of times you can eliminate one part of the integration or stuff because it's symmetric. So when he says the probability, or he's asking for the region where the cosine is greater than 1/2, you have to figure out where that is. And here, it would be at pi over 3 or 60 degrees. And over here, it would be at minus pi over 3 or minus 60 degrees. So this is the range from here to here. So now you've got to find out, well, what's the probability density function for beta, right? We know the range, and we want to see the probability of, we got to integrate the probability density function from here to here. So now we got to get the probability density function of beta. And remember, beta is equal to theta over 2 minus psi over 2. The order makes no difference. Now, that is something where they are uncorrelated, and this is like of the form that z is equal to y minus x. So you know you can do convolution. Now, that was the one point I was really trying to get through in section 3.4 and 3.5. If the density functions are independent, if y and x are random variables that are independent, then if you have z, a third variable, or beta in this case, is equal to y minus z, it's convolution. If it's y plus z, it's really going to be correlation, or it's the same form of the integral, but now it's kind of one of these things, instead of the function of with a minus sign in there, it's going to be a plus. But so when you do this, now you can do this kind of interesting. I know what I'm going to do is take f of theta over 2, and he does say it's convolution times f of psi over 2. Those are the density functions I showed there. This is the standard boxcar, right? And when you flip and shift one through, they're both the same. So if you do convolution, what happens? You're going to take one of the functions and leave it alone. You can put this versus tau. And this is going to be at pi, height 1 over pi, right? And then you take the other function and flip it, and let it move through, and this is going to be, I'll call this f of theta, and this is going to be, and I'll use tau here. I could use y, but maybe I will use y. F of theta over 2, and this is f of psi over 2, but now the argument is going to be, sorry, not y, it's got to be tau or x or whatever, tau, and this is y minus tau here, and this point is going to be y, and this is going to be y minus pi at the lower end, and you're integrating through. Do you remember you get the overlap area in class? Yeah.
I thought it was a z equals x, a theta plus y, theta x plus y.
Yeah, but no, it's the argument inside there, though. Remember, beta is this. This is what we're doing. That you're looking at the. We got a from that, but the fundamental form is there. See, we got the range. Hold it. We got the range once we had a, right? A defined. Then we got the range of beta. Remember that? We said a greater than 1. A was 2 times the cosine of theta minus psi over 2. Do you remember that? So this is what we have to figure out. What that implies is we need the probability density function for this. Remember, we need to figure out what's the probability density function for beta so we can take it and integrate over that area from minus 60 to plus 60. And I'm trying to show you the convolution. Remember, we've got two identical functions, boxcar functions. We're going to convolve them. I know the width is going to be 2 pi. When we take one of them, right, it's really take the overlapped area and then integrate, take the overlap region and integrate the area there. As it moves through, it hits a peak right at 0, by the way, because this is going to be time delayed. This is going to be delayed by minus pi. And then it's going to go to 0, and he shows you what it looks like. If you know your Laplace transforms, you can do this fairly quick. This is called pulse functions. You're convolving 2 pulse functions. In doing so, you're going to get a tau over 2 sinc squared of pi tau over 4. And then when you go back the other way, it's a triangle function. Trust me, it works. But if you're not familiar with that, don't spend time because you'll get yourself more confused. If you do the convolution, here's what happens. It goes from minus pi to pi, and it does this. And here it's going to have a height of 1 over pi. And this is my f beta, and now the argument is beta, right? Correct? I wouldn't make the functions sines and cosines, but it surely could give you a problem like this. Just change it from sine or cosine, something that's just a constant value or maybe a straight line. Something a little more easy to get the form of a, because that trig identity takes some time to see. So we want to find out from minus pi over 3, that would be 60 degrees, to plus pi over 3, which is 60 degrees. We want to figure out this area. Isn't that the probability? So if that's f of b, if we want the probability beta is greater than minus pi over 3, less than pi over 3, what I'm really going to have to do is integrate from minus pi over 3 to pi over 3 of f beta of beta d beta. That basically would do it. That's what I'm trying to tell you. Now, how are you going to do that? Well, I don't really care. Here's one trick. You guys got crazy calculators. If you can write an equation for those lines, you can do it. You can just take it's 2 times the area from here to here, right? Or you can flip it and just do this. This is 1 over pi. I'm going to show you another trick. This is pi. So I know the area here is going to be 1/2. If it's 1/2, what I can do is this. I can say, I know I'm going to take, if I take the area from here to here, right here, I just multiply it by 2. This is half of the actual area, total area of 1. So what I can do is go like this. I can go from pi over 3 here, and I can take 1/2 minus this area, right? There's several ways to get this. Do you agree with that? Then multiply that by 2, right? Or you can do this, and this is scale. This is a simple trick. All right, that has a scale of pi linearly. This is a 1 over pi here. What I can do is get rid of the pi's, and the reason is they appear in the same way. The multiplied product, what I'm about to show you, is going to be the same. Here it's going to be -1. This is 1. The height of this is 1. And this is my new functional form. I scaled everything. With me? Now, instead of pi over 3, minus pi over 3, now I'm going from -1/3 to 1/3. So it's this. Here's the area right here. With me? If I take the total area, that's 1, minus, all right, total area is 1. And if I subtract this area and this area, I'll have the remaining. What's this area? Well, this is the height of 1/3, agree? I mean, we can do it. It's a linear scale. All right, slope is, so it's 1/3 height, 1/3, right? So this width here is going to be 2/3, right?
Yeah. Oh, yeah.
Actually, you know what? This is 2/3, my bad. This is 2/3, correct? So if I take a look at this area, it would be 2/3 times 2/3 times 1/2. And I have to add this area, which is 2/3 times 2/3 times 1/2. Or it's just 2/3 squared. So if I take 1 minus 2/3 squared, that would be the actual probability, the area associated with the probability of this occurring. And that's equal to what? Well, that's 1 minus 4/9, which is 5/9. And I think that's the. Then he has something else. Here's the probability density function right here. From minus pi to pi, here, 1 over pi, and what does he say, King? So this one, A.
Less than or equal to 1/2.
So I can say 1/2, and that's less than or equal to A. And since A is equal to 2 cosine of beta, I'm just showing you the technique I use. So that means what? If I go ahead and divide by 2, I get cosine of beta less than 1/4. This is in pi. This is going to be 180 degrees, and this is minus 180 degrees, right? So I think this, if you take the inverse cosine or arc cosine of 0.25, I think it's
75.52
all right.
degrees.
So we go from minus 75.52 degrees to 75.52 degrees, right? And he says less than that. Well, that means if you think about the cosine function, if it's less than that, we got to move out a little further and come to about here and here. And what we need to do is now figure out the probability of the angle less than 75 or greater than 75.52 degrees. That would be this area added to this area right here. Agreed? Or twice either one of those two areas. If I look at a scaled version of this, right? I'm going to go height 1, 1, minus 1. Now, normally I divide everything on this axis by pi. So if I have 75.52 degrees, and I want it in radians, right? I think it's 1.138 or something like that. So I take 75.52 degrees, then I multiply it by pi and divide it by 180. What's that number? 1.318? Now that's radians. Now the trick I use is you got to divide that by pi again to get this point on the axis. With me? Remember how, if I wanted to use the scale triangle, the horizontal axis you divide by pi, the vertical axis you multiply by pi. You with me? It's just a scaling thing. So divide 1.318 by pi, 0.42, and I'm going to bet, here's what I want. I want the area here plus the area here. Agreed? The slope of this is 1. That's the reason I love doing scaling with this. Okay, so what I really can do is take this distance here times this distance here. Now normally I take this times a half, then I take this times a half, but why not just take this times this? Shouldn't that be the same? What's this distance? Well, that's 1 minus 0.42, correct? This is a 45-degree angle. That side has to be the same. So square it. You tell me what you get. 0.3364. I didn't either. I'm pretty sure that's right. I think that's a mistake, so mark that down. Let's make sure you don't go nuts if you don't get his answer on that one. Leaving the station, you got a commuter coming to catch the train. So the probability density function for the commuter's arrival, get rid of the 8 o'clock, is this. I'm going to call it f of x. We're going to call x the commuter. And y is the train. For the commuter, from minus 5 minutes to plus 5 minutes, forget about the 8 o'clock, it isn't going to have a bearing. The height of this is 1/10. This is the probability density function for the commuter's arrival time. Now, underneath this, now we have the y, the f of y. This is the train's departure time. And it goes from 0 to 10, and it has a height of 1/10. So we have two variables. Now, this has a random variable x associated with it, and this has a random variable y associated with it. What we really need is the probability density function relating the, he wants the commuter's arrival. So he's going to have x, go ahead.
At the station in the train's departure time.
So he wants this. We'll just call this z. What do you know z's, the density function of z is going to be? You're going to have x minus y equals z, which is exactly what you want to apply convolution. Right, so this is what? It's an integral, right? Now you're going to have the first variable, which is a dummy variable. So this is going to be just y, and y goes from 0 to 10 to f of x, c plus 1. That isn't turning out like a convolution integral. I'm doing something wrong here.
That's right.
dy. If you look at this though, the problem is this should be z minus y for the convolution. For convolution, just take f of y, it looks like this. F of y. Now with this one, you don't do a flip and shift, right? That's f of z plus y. Normally, if it would be f of z minus y, you got to flip it, get f of x minus y, then you have to add z to it. So what this one looks like, this is my f of x. So it's going to be shifted down, so when z is minus 5, the window starts in. The window here is going to be 5 plus z, and down here it's going to be minus 5 plus z. It still has a width of that. The height is 1/10, and this is f of y of z plus y. But here I'm saying it from minus 5 greater than z and less than 5. So if you can follow me, if you look at this definition right here, I have fx of z plus y. So that's this function right here. Now, when you go ahead and put f of x of z plus y, if z was 0, it would be from minus 5 to 5. But when z is equal to minus 5, it just starts getting overlap area. Makes sense? And it's going to keep getting that overlap area, and it's going to get a peak right here to 5. And can you all see this boxcar moving that way, class? So that overlap area is going to grow linearly. I'm just going to tell you, out of time. For this one, it starts at minus 5, and it's going to grow, and it's going to hit a peak here at 5. And then it's going to start decreasing. Remember the width, they're both 10, so the width has to be 20, and this is going to be plus 15. This will be my f of z, all right? So if you take a look at this height right here should be 1/10 too, I believe. Y'all follow me on this? And this would be z. This is my fz of z for that definition, but I'm going to just say again, this is correlation, not convolution. We haven't even got to correlation yet, but it's similar to convolution, but instead of flipping the signal, you don't do that. You simply just shift over the second thing you're doing a correlation. You don't have to flip it with a graphical convolution.
As the probability that he will catch the train.
Commuter arrival, right? Train departure, right? As long as that's positive or is greater than 0, doesn't he catch the train? What's that going to be? It's all this area, right? Or take 1 minus this area. Your probability that z is going to be greater than or equal to 0, that's going to be 1 minus, and this has a width of 5, this has a height of 1/20th, and there's half of it, so it's 1/2 times 5 times 1/20, and that is 7/8. Is that right?
That's right.
All right, what's the next part of
The
it?
commuter is delayed 3 minutes by a traffic jam on the probability that the train will still be at the station.
Z now is 3. All right, so what you got to do is say the probability that Z is equal to or greater than 3. Now I've got to say, here's 3, right? So this is the area I'm trying to calculate right there, right? How would you guys do this? How about take 1, right, minus this area? So it's equal to 1 minus, now what's this area here? Well, the span on this is going to be 8 from here to here, right? And really it's going to have a 1/2 right off the bat. So I have 8. Now what's the height of this? Well, if it's a full span of 5, the height is 1/10, right? So if it's a span of 8, it's going to be this. See, if you would take, normally if I take a look at this, the height is 1/10. You could figure out the slope of this line. This is a factor of 10, so it's 1/10 over 1/10. It's going to have a slope of 1/100th. This is 8, right? So the slope, 8 over 100. So what is that? 1 minus 0.32, so I got 0.68. For the test, for the exam, it's 4 to 5, I haven't made it out, 4 to 5 questions. The conditional probability is going to be on it. Where I'm going to grab everything from is the homework. Definitely section 3.5 is on it. I mean, this last stuff we did definitely is going to have at least one problem. Some of the problems will be really related to prior stuff as well as section 3.5, or at least one. Feel free to use Laplace transform if it's convolution, like problem 3.5. So in chapter 3, we had distribution functions that are given as functions of x and y in conditional probability of f of x given y, f of y given x. It's Bayes' theorem to use it. Definitely going to get something on that. The expected value of x and y, if they are uncorrelated, it's the expected value of x, or if they are independent random variables, it's expected value of x times expected value of y. And if they're not, then you have to use the conditional probability stuff that we talked about, correlation coefficient. This is in section 3.4. Now, you're going to get a problem about correlation coefficient. You're going to get a problem from section 3.5, related to section 3.5. And probably the joint density fills that in, right? Okay. And remember, if you have capital F of x, y, and you wanted small f, or the probability density function of x, y, then you have to take a derivative of the actual cumulative distribution function with respect to x and then respect to y. Back to chapter 2, Gaussian stuff. You know you're going to see something using Gaussian and Rayleigh. I'm not going to give anything with Maxwell-Boltzmann. The uniform density function, I think it's pretty straightforward how to get stuff, but also with moments of the Boltzmann equation, or just the general expected value. Remember, the expected value of x squared is the sum of the variance, or the standard deviation squared of x, plus the actual mean value of x squared. Know that very well, okay? And you'll be using that. I would do the exercises, and some of the exercises have wrong answers, but in chapter 2 and 3, most of that stuff is, that's the meat of everything. Now, Venn diagrams, I'm not going to ask you a Venn diagram per se, but I may ask you what's the probability of like rolling a dice 4 times and getting an outcome of, if you added the values of each die, say it rolled a 1, a 5, a 6, and another 6, so you'd have 18. What's the likelihood of rolling 18? So then you have to figure that out. But remember the extra binomial coefficient. Yeah, for Bernoulli trials, this is section 1-10. Remember, if you're the probability of finding or getting 3 positive outcomes of 5 trials, remember that? Would be n factorial over n minus k factorial times p to the actual k times 1 minus p to the n minus k. That, I'm going to ask something about, I haven't decided what, something related to what we've been doing. Know that one, I'm not going to give it to you. Binomial coefficients for Bernoulli trials, it'll be in one of those 2 sections. And the last thing I'm going to say, I'm not going to ask you a Venn diagram problem. Here's the last thing I'm going to say. Remember the switching problems where you have switches in parallel, switches in series, probability of switch being closed versus, I'm going to give you a problem like that. And I haven't made it up. I haven't made any of this up. But everything's based on the homework. I'm not going to give you something as crazy as the problem 3-5.3. That is a long problem. If you're going to use Laplace transform, it's like for that problem in section 3, problem 3-5.5. That should be something you don't need tables for. 2 exponentials convolved, right? It's 1 over AS times 1 over BS, partial fractions. That should be something you can handle. But I'm not going to give you anything too crazy. I'll tell you what, for the Rayleigh, everything with sigma is related to Gaussian, all right? So I will give you the Rayleigh mean in terms of the Gaussian mean.